So now you have two measurements, MAD and variance. Obviously, they share some similarities, so they are both calculated based on deviations from mean. We do some adjustments to make sure that all the numbers are non-negative, and then take some kind of average. For MAD, the adjustment is to take the absolute value. For variance, it's going to take the square root. The square. So we can see they are somewhat doing the same thing with different principles. MAD puts the same weight on all the values, while a variance puts more weight on extreme values. Okay, on extreme values. For example, here, when we see the 5 numbers here, we see that their deviations are -5, -1, 0, 1, and 5. Then the absolute deviations are 5, 1, 0, 1, 5. And when we calculate MAD, each of these numbers have the same weight, So that gives us 2.4. But when we do the square, that means 5 becomes 25, while 3 would just become 9, 1 would still be 1. Okay? So if a number is originally large, when we take square, it will become even larger, relatively even larger. And then when we do the average, those extreme values would really count a lot. Okay? So a variance puts more weight on extreme values, or we can say a variance would be affected more by extreme values. Okay? And then we can also see that for two different sets of data, MAD and variance may tell you something different. For example, if we have another set of data here, 1, 2, 5, 8, and 9, we can see that for MAD, the second set is larger, but for variance, the first set is larger. Okay? This is, of course, possible because the formulas are just different. So when you have two sets of data, you need to decide whether to use MAD or to use variance as your measurement, because these two measurements may tell you different things, may rank variabilities of the two sets of data differently. Okay, so you need to make a choice. How would you make a choice? In some sense, it's up to you. It's up to you. For example, if you think that all the values, all the deviations should have the same weight, are equally unacceptable or are equally serious, then you would use MAD. If you think extreme values or extreme deviations are really a big deal, then you should use variances. Okay? In general, people use variances more than MAD. So that means if you don't know which one to use, then probably you want to use variance, because variance is more common than MAD, or we can say variance is more common than almost all other measurements. Okay? But you should know that MADs are still popular in some areas, for example, demand forecasting and something else. So it's your job to decide which one to use, and for example, sometimes you may want to see how other people in the same field or doing the same job decide which one to use as your reference. Okay, one drawback of using variance is very clear, is that the unit of measurement is the square of the original one. Okay, for example, when we talk about the baseball team heights, then if we really calculate the variance, the variance of member heights would be 34.05 centimeters square. Okay, it would be very weird to use centimeter square something to talk about heights. Okay, because it does not contain any physical meaning. So some people would prefer to take the square root of a variance to generate one other measurement called standard deviation. Standard deviation. The standard deviation of this set of data would be the square root of the variance, which is around 6 centimeters. So typically, a standard deviation can have more managerial implications. One thing that we can find immediately is that for two sets of data, if one has larger variance, it must has larger standard deviations, okay? Because it's just taking the square root. So variance and the standard deviations, they have one-to-one mapping, and you somehow can say they are the same measurement, because when one is larger, the other one must also be larger. Okay, it's just that the standard deviation has more physical meanings, because once we take the square root, the unit of measurements becomes easier to understand. Based on standard deviation, we can define something called z-scores. Suppose we have a set of sample data with sample mean x bar and the sample standard deviation small s. Then for each value xi, we define its z-score as this. What's that? The numerator is xi minus x, so that's the deviation from mean. And the denominator is s. So we are using the deviation from mean to be divided by the standard deviation. That gives you zi, which we call it a z-score. If it's a population set of data, then basically everything is the same. Mean is mu, population standard deviation is sigma, and then the z-score formula would become xi minus mu divided by sigma. But you know the principle is just the same. A value's z-score measures how many standard deviations it deviates from the mean. We want to know how far it is from the mean. But here we are using standard deviations as the unit of measurements. Obviously, that's because when a set of data is more dispersed, then the variance or the standard deviation would become larger, right? So if you want to, for example, compare two sets of data, within two sets of data, within each set, you get one number, and you calculate that deviation from mean, okay, for x1 and for example, y7, then that numbers do not really help you anything about comparing the deviation from mean, because the two sets of data, they may have different standard deviations. Okay, so the action of dividing the deviation with some kind of standard deviation is to what we say is doing some kind of standardization, so that you can make the comparisons be on the same scale, or at least on some similar scales. Okay, so these scores can be useful when you want to compare two values deviations from mean in two sets of data. Moreover, z-scores is used in a traditional sense to detect outliers. Okay? For detecting outliers, one common way is to check whether xi satisfies this, or we can say whether a value's z-score magnitude is at least 3. Okay? If you have a number, that number deviates from the mean for more than 3 standard deviations, we say it has some chances to be an outlier. You should check whether it is an outlier. Okay? Why? You probably want to do some experiments by yourself, or wait for some examples that we will give you in lecture problems. But you can see that it is quite rare for a value's z-score to be so large, or so small, so negative. Okay? It's just uneasy for that to happen. If you randomly generate a set of data, it's not so easy for a number to be so far from the mean when you do the measurements in standard deviations. Okay? So that means that number would be very extreme, and the extreme values may not be outliers, but you may want to double check whether there are some problems there. Okay, so that's the principle. And if you are talking about sample data, of course you will use the sample data formula for z-score. Some people say that this is okay, but this is not a very good idea, not very scientific, because mu and sigma actually are affected by extreme values. Okay, so why would you use some measurements that can be affected by extreme points to detect the extreme points? That's not make sense. So some people say, how about we use median and MAD? Oh, sorry, this should be MAD. Okay, because if we do that, then these numbers are not affected by the extreme points, extreme values so much. Here, it's actually very interesting because this MAD can be many things. You can do the mean absolute deviations from mean, or mean absolute deviations from median, or median absolute deviation from median, something like that. No one says one is better than the other, definitely, okay, because you can see that all these measurements are just intuitively right, but hard to say whether one can be always better than the other. So in any case, please remember that all these rules are just some rules that somehow suggest you some numbers to look at. Okay, some numbers to look at. But satisfying these rules does not mean that number is an outlier. Okay, nor it is necessary for an outlier to satisfy these numbers, these rules. Okay, so they are just some giving you some suggestions, but it's the analyst's responsibility and job to really use whatever ways to try to detect outliers. Okay, these are just some minimum level thing that you should do. Okay, so again, we have population and sample. So the formulas for population and samples can be different. For sample mean, we have mu and x bar. They are different. Okay. For population and sample variances, they are also different. Okay. When we were doing really the average of all the squared deviations, we are actually calculating the population mean. Okay, for population mean, we divide the sum of squared errors by n. But when you do sample variance, we divide the sum by n minus 1. So please note the difference between n and n minus 1. That's really different. If you use the wrong denominator, you will get a different number. Okay? And then you of course know population and sample standard deviations would be defined also with n and n minus 1 as the denominator. So that's also different. We will tell you why we have this weird minus 1 in the future. We cannot do some rigorous proof to you, but we will intuitively tell you why is that when we talk about inferential statistics. Okay? At least, please pay attention to the notations. Sigma, sigma square, s and s square, they are used around almost everywhere in the statistical world. Okay? So starting from now, when you see s, when you see sigma, when you see s square, when you see sigma square, you know what do they mean. Finally, the last measurement of variability is coefficient of variation. It's simply the ratio of the standard deviation to the mean. like this, okay? Or if you talk about sample data, then it's S divided by X bar, okay? Very intuitively, please think about why would you try to use coefficients of variation, okay? Why would you like to adjust your standard deviation by mean? Oh, obviously, there are some reasons, and let me try to leave it to you. And if you really need some discussions, let's discuss it in class. Okay, thank you.